Okay, let's get started today. Y'all are subdued today, maybe because it's a cloudy day. But at any rate, who knows? Usually you're all quite talkative. We are going to be finishing up with functions. So what we're actually doing is some string stuff with find and substrings. So these are functions you saw in CS102 but probably have long forgotten about, and they can be useful. And then we will be moving into classes, which you also covered toward the end of CS102 and which will be an integral part of this course. And we have a whole bunch of things that we'll be talking about over the next 2 days with classes. When we get there, I will give you some of the items we'll be going over. There's kind of a whole laundry list. And really the next 2 days are kind of also about just bringing together a lot of the ideas that we reviewed in the first month of this course. And then starting next Thursday, we're going to be moving into the first of the data structures of the course, which is hash tables. So that's kind of a roadmap for where we'll be going in the near future. I did get a good question from a student who was worried that the participation activities for this week, even though the student had completed all of the assigned participation activities from the CS140 website, it still wasn't coming up as 100, and that's because I didn't assign all of the participation activities from section 15. And the same thing, today I didn't assign all the participation activities from 16.1 and 16.2. I'm going to go back probably tomorrow and adjust the grades because I know that that's the case. So don't worry, the grades will get adjusted this week. So if you think, wow, I finished all the participation activities that were assigned but I didn't get 100, why is that? Just I need to adjust the grades and I'll do that tomorrow. And then also something about Lab 3. Know the TAs might have gone over it, but it's kind of a hard concept, so I want to go over it as well. It's on the padding and the cropping. So there's two programs you're asked to write in Lab 3. So the one with pad says you start out with some image like that. And what you want to do is pad it with some number of pixels on each side. And we said you can't use a second vector for this. You have to use the original 2D vector. And the reason is we don't want you wasting space. You can do it with the original vector. So with pad, what you need to do is first you have to resize the 2D vector. And I'm not going to tell you how to do that because we want you to figure it out, but you need to resize the 2D vector so that it's large enough to accommodate the padding. Then the next thing that you do, and this is the key insight, is the way in which you are going to copy your pixels. You may well be inclined to say, okay, let's start at the upper left corner at 0, 0. And let's say that the padding is equal to 5 pixels. If the padding is equal to 5 pixels, where should pixel 0, 0 go? Okay, actually 5, 5. Okay, we think about it. The padding, here's 0, here's 1. So here's 1, here's 2, here's 3, here's 4. So 0 through 4 are padding. So the pixel is going to end up 0, 1, 2, 3, 4 is going to end up being at 5, 5. It should be right there. And that'll give you 5 pixels of padding. See, 0 through 4 and 0 through 4, they both give you 5 pixels, right? Now, so 0, 0 should go to location 5, 5. What happens when later I get to 5, 5 here and I try to copy it? And we're part of the same vector. This is part of the same vector. This vector and this vector are the same. What's going to get copied when I copy pixel 5, 5 over here to its new location? Yeah, the problem is I overwrote it. What pixel 5, 5 contains is the original pixel at 0, 0 because I already stored it there. 5, 5 isn't the original pixel that was there anymore. Okay, so this is why I said key insight. You can't start at the upper left corner of the image, because if you start at the upper left corner of the image, you're going to end up clobbering, as you move items, you're going to end up clobbering parts of your PGM. So can anyone think of a possible way to get around that? Start at the bottom right corner. So the key insight is to start at the bottom right. And do the move. Okay? And it's going to turn out that it doesn't really matter whether you move the last row or last column. It's up to you. Actually, it does. So I'm not going to say it doesn't matter whether you move the last row or the last column. So think back for a moment. There is, from a correctness standpoint, it doesn't matter whether when you do the move, let's get a fresh picture. So what I'm saying is when you are doing the move, you'll take either the last row and move it first over to its new position, or you will take the last column and you will move it over to its new position. So basically you're moving either the last column or the last row. Which way do you think you should do it? Do you think you should move the last row or the last column? And I'll tell you, both of them are correct. They'll get you the correct result. But one is more efficient. The row. Very good. Why? You have it as a vector of rows. So the row is contiguous. And that means it's all in the same cache line, meaning you're getting lots of cache hits. If you move the column, each pixel in the column is in a different row vector. And the computer may be all over the place, having cache miss after cache miss, and having to go out to RAM in order to find the pixels in the column. So you actually want to move it by rows. Even though both are correct, it's more efficient to move it by rows. So the key insight is to start at the bottom right corner and move by rows. Okay? And for absolute safety, start with the last item in the row and work your way to the left. So the best thing you'd start with this pixel and you'd move it over here. Then the next pixel you'd move to your left. And that will give you the absolute most safety. So right to left. Questions about that? Okay. Now, Crop is different. So with crop, what you're doing is you're taking some portion of the PGM file and you are moving it to the beginning. Now your intuition would be right if you say to move from the upper left corner, because you want to move this pixel into its new location, then this pixel. Now with crop, if you start it from the bottom right, it could be a problem. If I first start it from the bottom right, it might actually end up overwriting something in the existing PGM. So with crop, you also you can't resize initially. What happens if you resize immediately? You lose it. If you resize immediately, let's say I want to crop to there, and I immediately resize, I lose it. So here with crop, you also can't immediately resize, or you will lose the potentially part of the PGM that you're moving. So you actually, in this case, move first. So you move the topmost row. Well, start at upper leftmost pixel. And working left to right, move the topmost row to its new location. Okay, repeat with the remaining rows. Working your way down. And then finally, resize at the end. And this way you can do it without actually using a second 2D vector. And that's what, again, we're interested in teaching you in this course, is how to do things efficiently and with the least amount of memory. So with crop and pad, your initial inclination would be, oh, I'll just create a second 2D vector and copy the contents of the first vector to the second vector and then copy it back. No, that's super inefficient. Okay, you can do it with the original 2D vector. So in some cases I bold-faced it, but make sure with each program you look carefully at the directions, because each program has some constraints as to what you can do with the vectors, whether you can use another 2D vector or not. If it says you can't, and you do, you will lose points. Okay? So questions about that? Yes?
You said resize the vector at the end. Did you mean just at the end of moving the pixels?
Yes, at the very end.
Okay.
Okay, so resize the 2D vector at end of moving all pixels. Because if you do it at any other time, you can lose part of the image before it's been moved. Okay? Other questions about that? Okay. In that case, what I want to do is to talk briefly about a couple useful things about strings. Now you may remember already a couple useful things. Dot size returns the number of characters. And you can treat a string as a vector. So you can access the individual characters. Now there are a couple other useful functions that you might wish to use at times. One is called .substring, and it takes two indices, begin and end, and it returns the string substring starting at begin and ending, this is important, n minus 1. So it doesn't actually include end. If you want one character substring, like at character 3, you'd say 3 comma 4. Okay, so that...
I thought end was supposed to be how many characters?
You may be right. Actually, let me check that. Shoot. Right before here I was. Let's check that quickly. Yeah, you're right. Sorry. I was in the wrong language. Okay. So it is the number of characters. So, we'll redo this. Thank you. It is actually length. So returns the substring starting at begin and having length characters. And if you omit length, this is optional, then it will take it to the end of the string. So the second parameter is optional. If you omit it, it goes to the end of the string. And then the fourth useful one is .find. It takes a string and it returns the index of the first substring matching it. So returns index of first character that starts a substring which matches string. So let's say that the string is hello Brad and hello Brad. If I say .find, so if this string is, let's say, an S, and I say s.find Brad, it will return the index of that B, which is at 0, 1, 2, 3, 4, 5, 6. So s.find returns 6 because that's the index of the first character that starts the substring which matches Brad. Okay, so that's useful for finding where things are in a string. Okay, now Dr. Planck uses these functions in a number of ways in his notes from last time. And for the most part, I think that it's self-explanatory, so I'm not going to go into a lot of detail. He's basically, Dr. Planck's a music buff. He has this playlist with titles of songs and their length, and he's pretending that he wants to cut a number of CDs. And each of the CDs, I believe, has 80 minutes of storage capacity. So he's got to cut these every 80 minutes, or he doesn't want to truncate a song. So if a song would go past the 80 minutes, it goes on the next CD. And he guarantees that there are at least 2 spaces between the title and the time. or its length. And that's important. Okay? It's important because he wants to be able to easily get the entire title with one shot. But the problem is there's often spaces between the words in a title. But he's going to guarantee there's only one space ever between the words in a title. So if he ever gets to a point where there are two spaces, he knows that's the end of the title. So in this case, two spaces marks the end of a title. So that implies that two spaces denotes the end of a title. Okay? So he's going to be reading these a line at a time. He can't use CN to read them because CN is only going to get the first word of a title, and he needs to get all the words. So he's going to read a line at a time. Whoops. And then he needs to separate the title and the time. And he can't really use a string stream for this either, not easily, because it's going to keep reading a word at a time if he uses a string stream, and although this looks like a number, it's not a number. So if he's trying to say stop when I reach a number, it never will, because none of those things are numbers. Okay, and you can see there's actually can be numbers in the input or in the title. So you can't rely on a number being denoting the end of a title. So instead, he's going to use two spaces, and because he can't use a string stream, he's going to have to use the substring function. So he can search first using find for the first place that has two characters. Okay? So here, with Africano, it's going to be 1, 2, 3, let's count it out, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 is going to be what's returned by find. So if he wants to now set title equal to, let's say the string is S, he's going to take the substring, and where is he going to start? 0. And where can he end? At 8. Which is location. So he can take the substring starting at 0 and going to location, and that will give him the entire title. Does that make sense? Okay. Then he somehow has to be able to find the start of the time. And what he's going to do is he's basically now knows that there's all spaces. So he's going to now treat it as a vector, and he's going to just keep searching until he gets a non-space character. So he's going to go until he gets the first non-space. So treat the string as a vector. And search from loc. Remember, loc was the value returned by find. Search from loc until you locate a non-space. Then he's going to do some extraction with this string. Okay, how can he extract that string once he knows the index of the first character? Let's say the index is first char index. How can he extract, and the string is S. S is the string that contains the whole thing. How can he get 510 out of there now? He already has done effective find. He knows first char index contains the index of the first character, which is 5. Substring, so he's going to do substring, starting at first char index. Do we need a length? Seems kind of dicey because here the length is 5 and in other places it's 4. But we don't need a length because remember, if we omit the second parameter, it simply returns to the end of the string, which is perfect, exactly what we want. He's guaranteeing that there's no spaces at the end of it. Okay, so that's how he extracts the two fields. He's using a combination of find and substring. So let's just take a quick look at that. So this is the code that he's using to extract the two fields. He gets a line at a time with getLine. He uses the find to give him the index of the first character that starts a 2-space interval. Okay, he does his normal error checking if such a thing doesn't exist as a bad line. Otherwise, he pushes back the title using the substring function. Then, as I said, he is going to keep going until he encounters a non-blank space. So he's treating the string as a vector. And then he's pushing back the time by taking a substring starting at I and going to the end. So that gives him his two fields, the song title and the timing for it. Now, the other thing he has to deal with is the matter of every track is, I believe, or every CD is 80 minutes. Okay? Which means this isn't a very good way. You can't really add things this way. The computer doesn't have arithmetic for minutes and seconds. What you're going to have to do is first calculate how many seconds are on that track, which is 4,800. Not on that track, on the CD. So each CD is equal to 4,800 seconds. Then he has to convert each of these to seconds. Well, you know how to do that. How do you convert 510 to seconds? Just you. How do you convert? Yes.
You multiply 5 by 60.
Okay, so you multiply 5 by 60 and you add 10. Which means you have to extract the minutes part to multiply that by 60 and then add 10 to it. Okay? So we have a string of indeterminate length because we don't know how many minutes are on the track. Okay? So he does have his string, however, and he can either use the find function, so he's got the time. Now he just has to extract the minutes and the seconds. And he's going to use a trick. The trick is that he's going to replace the colon with a space. If he replaces a colon with the space, let's say, then it becomes minutes, minutes, space, seconds, seconds, and now he can read it using a string stream, because now he knows he has two numbers. So he's first going to find this colon, and he's going to replace it with a space. Then he's going to stuff this new string into a string stream and read the minutes and seconds. Okay, so let's see him do that. So he's using the find function for each timing. He uses the find function to find the colon. Then he treats the string as a vector. And notice now, because he put the timings into a vector, so each timing is in a vector. So now he has to give, this is the row number, and this is where the colon exists. Okay, so it's the appropriate row. If we're down here in row 2, then I would be 2, and the colon would be wherever the position of the colon is. He replaces it with a blank space. SS is an I string stream. The ubiquitous clear to make sure that we clear it before we stuff the string in. Read the seconds and minutes and do our calculation of seconds. And then at the end, he restores the colon. Okay, because that's important for the rest of his program. You still want to print it out as minutes and seconds. So he restores the colon at the end. Okay, so are there questions about what was going on here? We've seen, I guess I'll take questions in a moment. I just want to review. We first took advantage of the fact that there was more than at least 2 spaces between the title and the timing. So we used the find function to find the first space that was part of a multi-space sequence. That gave us the, in effect, end position of the title. Then we used the substring function to extract the title. That was 1. Then 2, we used the fact that this could be treated like a vector to iterate until we found a non-space. Once we had the location of the starting character of the time, we again extracted it using substring. Then the third thing, we had to convert the time to minutes and seconds. And we did that by using a trick. We replaced the colon with a space. When we replaced the colon with a space, it became minutes and seconds like that. And by stuffing the string into a string stream, we could now read the minutes and seconds as integers. Okay, because you can't tell a string stream, unfortunately, that the delimiter is a colon rather than a space. It would be nice, but we can't. String streams, NC in and C out all use white space, and you can't change that. I'm going to let you look at the rest of his notes on your own because I think they're pretty self-explanatory and you should be able to understand them based on what we covered with functions both on Tuesday and with what you covered with functions in CS102. But are there any questions about this? Okay. So it's time in that case to move on to classes. And there's a whole bunch of stuff that we're going to talk about as part of the next day and a half. So with classes, we're going to talk about access protections. We're going to talk about methods. We're going to talk about constructors. We're going to talk about header files. We're going to talk about separate compilation. We're going to talk a little random numbers. And you're going to see a little HTML. So it's got a whole bunch of everything. Actually, probably with these really aren't part of classes, so I probably should have pulled them out like that. Now, I'm not going to go through blow by blow with classes because you already read about them in the Zianti text. I am going to point out a few important things that you really need to remember. So, first of all, with classes, the idea is that oftentimes you need to store heterogeneous data, like the information for a driver's license. But not only do you need to store heterogeneous data, you want to do operations on that data. And a good example is actually Lab 3. In Lab 3, you have what really could be considered PGM objects, although you're not using classes in Lab 3. So I want to make that clear. You're not using classes in Lab 3, but in fact, you very easily could represent each PGM file as a class. And the operations that you're implementing would be the methods of that class. So you could easily think of something where you would maybe have class PGM and you'd have some protected data, which would be your 2D vector. So we have a vector of ints, which it might be the image. And you also have the rows and the number of columns. You might even store the file name. So you'd have some data that you would be storing for each PGM file, and then you would also have some public methods. You would have the constructor. The constructor, remember, is the name of the class, and then any parameters it takes. In this case, probably the PGM file would take the file name. When you create a new PGM object, you'd pass it the file name so it can read the pixels into the vector image and also jot down the number of rows and number of columns. And then there would be things like crop with its parameters and pad with its parameters and counterclockwise with its parameters and so on and so forth. So it would have a set of methods that would operate on the data. Okay, so you're going to use classes over and over again in the rest of this course. And in general, they're going to have a protected element which contains data and a public section that contains methods. And you'll often hear the public portion referred to as an application programmer interface. Or API. You'll almost always hear programmers talk about APIs. Application Programmer Interface. It's typically the public methods of a class, at least thus far. Application Programmer Interface, API. You will hear that a lot in your careers. Okay? Now, a second thing. The book uses private. Dr. Planck uses protected. Use protected. Okay, I'm going to put this in red. Do not use private. Private is very bad for something called inheritance. You won't really learn about inheritance until you get to CS 365, which is a junior level course. But suffice it to say that private has some flexibility killing elements to it, and it's just a horrible idea to ever use private. And it's unfortunate that the book chose to use private. Okay, protected, turns out, provides more flexibility. It still hides the data from the public, but it turns out that there's something called inheritance where you can create what we call subclasses of PGM. And if we create subclasses, those subclasses can look at the data if you declare it as protected. But if you declare the data as private, even the subclasses can't look at it, and that's disastrous. So declare your data as protected, not private. Okay. Now, we also cannot emphasize strongly enough that data should be protected. You don't want to make it public in general. The reason is that you want to have the flexibility to change the implementation. For example, even though we're having you use vectors, because we want you to learn how to use vectors, they are not the most efficient way to implement a PGM image if you know the rows and columns in advance. If you know the rows and columns in advance, which you would once you read the file, you could create a 2D array, which is more efficient. So maybe down the road, I would want to change the implementation from being a 2D vector to a 2D array. But if I made the data be public, then programmers might be relying on me to use a 2D vector. Well, once I change to a 2D array, their code won't compile anymore. It breaks their code. We don't want that to happen. So the advantage of protecting the data is that we're able to do what is called modular implementations. We can change our implementation without affecting the rest of the world, as long as we don't change the API. As long as everyone interacts with us through the API, then we can change the internal implementation any way we want, and we won't break anyone's code. So make sure that in general, you protect your data. You make your methods public. Okay? And then there are two terms that the book talks about, and we talked about in CS 102, and those are accessor functions and mutator, or accessor methods and mutator methods. So you'll hear these terms a lot. Accessor methods provide, in effect, read access to data. And in effect, mutator methods provide write access to data. They allow you to modify the data. Okay. Questions about that? Okay, so these are important terms, and I want to emphasize them because you'll hear these terms a lot. Now, before we go further, I'd like y'all to take probably only about 5 minutes or so, and we have a little in-class exercise that is, if you go to today's after-class exercise, you'll see that it is classes day 1, and it's going to take you to section, is it 3 or 4? 16. 16.4. So you're going to do the challenge activity in section 16.4, which is asking you to read some code and type its output. So I'm going to give you about 5 minutes to do that.
Okay, if you don't remember what it's worth.
Okay, I'm going to go over it. I don't know whether it's randomizing it or not. How many had 94 as their first number? It's random? Okay. Well, I'll just do one, and then to kind of, if you'd struggled with it, to give you the gist of the idea. So you had a class dog. You'll see it had two public functions, and it had a protected one, which was months. So we start it by defining a single variable buddy, and then we invoke setAge to set Buddy's age to 94 months. And you can see that setAge, all it does is it sets that variable to months to set. So setAge is what kind of method? Mutator. Very good. It's a mutator function. Okay, so it sets the months to 94. Then we print out the stage. So we're calling getStage. And going up to getStage, you can see it returns a string. And it is storing that string in the variable stage right there. So I had 94, so months is not less than 12, it's not less than 13, it's not less than 40, so Buddy must be a senior. And if I do it, whoop, what? Ah, that's nice. Well, we all like our little cookie for getting it right. Of course, it's now going to be different. Okay. So that was, at any rate, that was the way, that was just giving you some experience with code reading. And there was one other point I wanted to make. So the other point I wanted to make was that you don't see a constructor there. Does anyone remember what happens if there is no constructor? What gets produced? A default zero argument constructor that does nothing. But only if you don't have any constructor. Any other time, if you provide any constructor, then there will not be a default zero argument constructor. Okay. Now today, unfortunately, is mostly hearing me lecture because there's a fair amount of material, and unfortunately, I can't really, I kind of have to lecture somewhat on it too, because we've seen in the past that it confuses students. So the next thing that I want to talk about, so we've talked about access protections and methods. We'll talk about constructors on Tuesday. What we need to talk about now is header files and separate compilation. So up until now, for the most part, you've used exactly one file for your programs. This is about to change. In the real world, programs are enormous. Often they're thousands, tens of thousands of lines, and putting it all in one file would be detrimental on many counts. You couldn't have multiple people working on the file, which is what you need on a large project. It turns out that if you only modify one line in a file, you don't really want to recompile a million lines of code. That could take forever. So you typically are going to split your program across multiple files. And with classes, you typically put each class in a separate file. And you put the function declaration, the class declaration goes in a header file. You'll often hear them referred to as .h files because by convention they end with a .h suffix to indicate that they're a header file. So we're going to go now to Dr. Planck's roster program. Actually, let's go, instead of to his roster program, let's go to his roster program because it's different than the book. Okay, so Dr. Planck his way of remembering names is to print out well, actually not print out, but create a HTML table of student photos and their names, and then he tries to memorize them. So what he wanted to do was write a program that would automatically do this for him. So he would take students, he would have JPEG files for each student, and then he would have a list of the student names, and he would want it to be able to read in the names in the JPEG files and create an HTML table, which is what you see here. This is an HTML table with the students lined up with a certain number of columns per row. This is Henry Bataille is actually Harvey, Dr. Planck's dog. So you probably recognize other of your favorites there. So these are some of the folks that Dr. Planck likes, obviously with their names changed. Okay, so the first thing he's going to do is he's going to define a class called roster so he can do this for different classes that he teaches. And he's going to have a vector of names, and he's going to have initially two very simple functions, one to add a name to the vector and then one to print them out. Now, we're going to emphasize this again and again throughout the semester, and already we see people not doing it. You need to program incrementally. So he goes through and he builds up his program incrementally. He doesn't try to write the whole program at once, because if he does that, it's going to take a lot longer to debug. I often have students telling me how long it takes them to debug their programs, and I always think a big reason is because they wrote the entire program and then it became really hard to find where the bug was. Whereas if they just written a little piece of the program first and tested it, and then written a little more and tested it, and then a little more and tested it, believe me, you'll finish it a lot faster. It's one of the best tips I can give for how you can improve your efficiency and productivity as a programmer. Incremental development. So that's what he's going to do. Okay, now, he's defined this class, but you'll notice it only is the class declaration, variable declarations, and method declarations. He puts this into a .h file. Now he's calling them 01, 02, 03 because he's doing incremental development. In practice, you wouldn't put them in separate files. You would just create a .h file. By convention, we capitalize the first letter of a class. That's just kind of a convention to capitalize the first letter of a class. And then the header file is typically going to have the same name as the class. So in this case, roster.h. You only put the class declaration. There is no no method definitions. Remember that we say that a method declaration is simply the prototype. A definition is the function body. Okay, remember that? Because I will use that distinction. A declaration is simply the function prototype. A function definition or a method definition is the function or method body. So where then do we put the implementation for our methods? That goes in a CPP file that typically has the same name as a class. So each class typically gets two files, a .h file and a .cpp file. And I'm not going, really good form would be to capitalize these letters because they're also capitalized in the class. But Dr. Plank didn't do it, so obviously I'm not going to be particularly strict on that. But at any rate, the class name is going to be the name of the .header file and the .cpp file. So then in the .cpp file, you put your definitions for the methods. Remembering to precede your method names with the name of the class and 2 colons. Because if you don't do that, it has no idea, the compiler has no idea what class the functions belong to or whether the functions even belong to a class. Main does not belong to a class. And even though you put the functions in a file called roster.cpp, that is meaningless to the compiler. So you need to remember to put the class name in a double colon. You also will see this include statement. So you have seen include statements already, but they always had angle brackets. It was always things like include IO string. And they would use angle brackets. Now we're using quotation marks. So what the include does, first of all, is it includes that header file. It literally replaces the .h file with the contents of the .h file. So it physically copies the .h file into there. Okay, and the book has a good illustration of that. Okay, so the book has a nice illustration of how what we call a preprocessor. So the preprocessor, call it the preprocessor, copies the contents of the .h file into the .cpp file. So #include instructs the preprocessor to copy the contents of the .h file into the .cpp file. And if it's a user-defined .h file, you use quotation marks. If it is a system-defined include file, you use angle brackets. So in fact, when you've been doing your include statements, it has actually been copying declarations into your code. Like when you say include string, it includes declarations for the class string. When you say include vector, it includes the class declarations for a vector. And when you include an IO stream, it includes actually includes class declarations for IO streams and declarations for the variables cin, cout, and carr. Now, you put the functions for the class into a .cpp file. You put your other functions that are part of main into a separate file, which Dr. Plank is calling roster main.cpp. So we now have three files. The main file that contains main, the file that contains the class declaration, and the file that contains the method definitions for that class. You'll notice that in his main, he is also including the .h file because he's using the roster class in his main. And it's a very simple program initially. He's simply opening the file. I know that we're not reading from CN now. We're reading from a file. Expect you to remember that from CS102. If you don't, they are IF streams for an input file and an OF stream for an output file. The open indicates which file to associate with this file input stream. And in this case, that file is coming off the command line. We need to check to see whether the file failed to open. For example, we may have given an invalid file name, or we may not have read permission. Hopefully you remember this function PERROR stands for print error. It prints the last error message that was placed into a certain part of the operating system when an operation failed. So if the file open failed, it places an error message that is accessible by PERROR. And this is what precedes the error message. So PERROR will produce the contents of argv1, then a colon, and the error message. So whatever you provide as an argument to PERROR goes before the colon. And then he exits the program. Otherwise, he is simply getting a line at a time from the file, calling r.addName to add the name to the roster, and at the end he prints it. So he starts simple. All he's doing is reading them in and printing them out, doing nothing more, nothing yet dealing with an HTML table, nothing dealing with the JPEGs yet, just making sure he can read the file and print it. Now, he has to compile this thing. And again, here are the three files. There's the header file, which is included in each of the two .cpp files. Then, roster1 main contains main, and it uses the roster class, and it can only use the public parts of the class. Roster.cpp implements the methods for the class, and it's allowed to use both the public and protected parts. Okay, so the method definitions can use both public and protected. Now, we have to compile these. And the way we do it is by listing all of the .cpp files. You will note, and again I'll put this in red, no .h files are given to G++. Very often I see people putting .h files as part of the compilation. They no longer exist. The contents were physically copied into the .cpp files. The .h file is already in there. It's already in both of the roster.cpp and the roster main.cpp. It was physically copied into those two files by the preprocessor. So don't put the .h files with G++. It's just not necessary. So what this does is it compiles the two .cpp files and creates what are called .o files. So actually it creates a roster o1.o file and a roster o1 main.o file. These are what are called object files, and they are not executable. They contain machine code, but they can't be executed. Instead, they have to be linked together. So G++ is actually, in this case, a two-step process. It first compiles, and then it's going to link. And the book had a great example of it, so I'm going to go to the book very quickly. And here it is. So when it compiles two functions, or two files, so here's the two files. Here's one file, here's the file containing main. Main contains some references to functions that it doesn't use. Doesn't define. Those functions are defined over here in this file. So the .o file contains some references, and it has a table which is in effect the functions I use but do not define. And this one has a file, this .o1 has a table of functions I defined and where they're located. Notice each of them, actually, yep, they are potentially the addresses of where they're located in that file. So these are supposed to be addresses. So then what the linker does is it combines, the linking process resolves these references. So it knows this table is going to contain the fact that 3 int sums and printf aren't defined here. But it will find that 3 int sum is over here, and it will be able to replace this reference with an address. And in printf, it's going to go to C standard IO, and it will also find an address and will replace the reference to printf with that address. So that is the link step. And when you're done, final thing, and I'll let you go, when you're done, what you have is an executable file. We call this the executable. And that is an executable file. So next time, we will talk a little bit more about what separate compilation means. We'll go over constructors, and we'll go over how to create that HTML table that Dr. Plank wants.